An aeroplane leaves a runway and moves with a constant speed of v kilometers per hour due north along a straight path inclined at an angle arc tan 3/4 to the horizontal. Meanwhile, a light aircraft is moving due north in a straight horizontal line in the same vertical plane as the airplane. So they're kind of like in line, like one is eventually going to go potentially under the other one at a height of 3 kilometers above the runway. And the light aircraft is traveling at a constant speed of 2v kilometers per hour. At the moment the airplane leaves the runway, the light aircraft is at a horizontal distance d behind the airplane. Let's just get the diagram down before we do any more, because we're going to be finding the distance between the aircraft as a function of time. So I'm going to draw, right, this is actually a 2D problem because they're both, even though we're in three-dimensional space, because they're both heading north, we can just, consider that single plane so it's just basically a 2D plane overall. Okay, so I've got this horizontal runway that the airplane's going across, and then it takes off, and we're told it goes at a constant angle of arc tan 3/4. So what that actually means is that tan of theta, if this is theta, is equal to 3/4. I might as well straight away work out sine and cos because I'm undoubtedly going to use them. So draw a little triangle over here, 3 and 4. This is a 3, 4, 5 triangle. So sine theta is going to be 3 over 5, cos theta 4 over 5. Okay, and we're told that it's going at a constant speed of v. So I'll just add that on like so. So this is my first airplane. Maybe it's here at some point. And I've got my second airplane, and it's in the same vertical plane. It's at a constant height of 3 kilometers above the runway, and it's just moving horizontally. So I'm going to work in kilometers and hours throughout, so I don't have to worry about the units, that everything's consistent. Okay, I've got most things down. Let's just reread it again. That's fine. All right, the thing I haven't done, or I haven't added the 2v on. And then as the airplane leaves the runway, the light aircraft is at a horizontal distance d behind the airplane. So it's gonna, well, let's have the start. You know what? I did put a little dot to show where the airplane was at a particular point, but let's move it back to where it's taking off. And at that moment, we've got the airplane, the light aircraft, for example, here. And then this distance is going to be d. Now we're going to apply that because there is constant acceleration. In fact, there is zero acceleration. So that is just going to turn into s equals, or speed equals distance over time, essentially. But let's look at aircraft one. Now we could split it up into vertical and horizontal components and do them separately, and we are going to deal with them separately, but we can write them as vectors. So I've got s, but actually it's going to be a vector, then u, and then I do have v and a, but they're all zero. Well, sorry, a is 0, so v is equal to u. So actually I've just got s, u, and t, really. The initial speed is equal to the final speed. Let's resolve it into components. So it's going to be v cos theta for the horizontal component and v sine theta for the vertical component. Of course, I'm splitting it up like this. And I've already done some groundwork, so it's going to be 4/5 times v and 3/5 times v. And s is then going to equal u times t. The only thing I need to consider is where my origin is, and I'm actually going to decide that the origin is here. because like 0, 0 is here. I have to decide it somewhere, and now that will avoid my second aircraft starting with like a negative displacement. So actually, S is ut, but I need to add on like my starting vector, r0, for example, which is going to give me 4/5. Actually, I'm running out of space here. Sorry, one sec. Just let me move this down. I'm basically going to multiply that 4/5 and 3/5 speed both by t, and then r0 is actually going to be, in the case of the first aircraft, d0. So I'm going to get d plus 4/5 v times t, and then 3/5 vt here. Let's take a look at aircraft 2, the light aircraft. So now u is simply 2v in the horizontal direction and 0 in the vertical direction. So S, again, I'm going to use this formula. I'm not going to write it down again, just I'm trying to save a bit of space, but I'm going to get this time a different R0 because I'm actually starting at 0 in the X direction, but 3 in the Y direction. So it's going to be 2v times t at the top, and then this constant 3 here. Those are two position vectors for the aircraft. We're asked to work out the distance, and therefore we can apply Pythagoras. We can find the differences, square them, and add them. And you can see the similarity. So I'm going to go straight for it and do the first aircraft distance minus the second aircraft distance, because we'll find the magnitude. If it's negative and squaring it, we'll get the same thing. So apply Pythagoras. Or maybe I should find the okay, so I've got a position vector now. So maybe if I just do this in purple, got a vector here, and I've got a vector like over here. So if I want to find the actual distance vector, I'm going to be minusing them. So d will equal, and it will be, let's just, sorry, just checking the answer again, 6/5 vt. Okay, so I'll go with 2 vt minus d plus 4/5 vt for the top when I'm subtracting the vectors, and then consistently on the bottom it will be 3 minus 3/5 vt. 2 is actually equal to 10 over 5, and that's where we get the 6/5 from, because it'll be 10 over 5 minus 4 over 5, 6/5 vt minus d, and then 3 minus 3/5 vt. So d squared will then equal 6/5 vt minus d squared plus 3 minus 3/5 vt squared. I probably should just add that I'm applying Pythagoras. Let's just check, does that give the same answer? Oh, they've got it the other way around. They've put the VTs first. Okay, I'll write another line. Because you can just swap them around. It'll just make it negative if it was positive and vice versa. But when we square it, we get the same answer. There we go. Right, now we're asked, or given the distance between the two aircraft is never less than 2, by the way, that means that d squared is going to be greater or equal to 4 because d is going to be always greater or equal to 2 because it's never less than 2, so it's 2 or more. Find the range of possible values for d. Now what we've got here actually is it's d squared, but obviously you could take the square root, and d is varying with time. So v is fixed, d and d squared are functions of time. So the way that I thought to do it is to find the minimum value of d. Or at least the time when that occurs. Because it's, you can see eventually the aircraft that's going horizontally is just going to get further and further away. So d is going to approach infinity as t approaches infinity. But there's going to be a point where they're as close as they can be together, and we just need to ensure that that is never less than 2 kilometers. So we need to investigate the value of little d where that's true. So to find out the minimum value of d, or at least the time when it occurs, what we can do is differentiate, and we can do implicit differentiation here. Differentiate both sides with respect to t. We get 2d using the chain rule and times by dd by dt. And then again, chain rule on the right. So 2 times 6 over 5 vt minus d, that's the outside, times by the derivative of the inside, 6/5 times v. And over here, very similar, 2 times 3/5 vt minus 3 times 3/5 v. And this thing is going to equal 0 for the minimum, or for stationary points. What that means is that I can cancel loads of stuff out. So I'm just going to get 0 because the whole of the left-hand side is 0. And on the right-hand side, I can divide through by 2 and times through by 5. So I'll get 6v times 6 over 5 vt minus d plus 3v 3/5 vt minus 3. Yeah, so basically cancelled these out because this was equal to 0 and cancelled these out. What else can I do? I can divide through by 3v, so that becomes 2. And I can times through by 5. So when I do that, this is going to go, and this is going to become 5d. This is going to be go, and this is going to become 15. Let me expand the bracket now. So 0 equals 12 vt minus 10d plus 3 vt minus 15. That means 15 vt is equal to 10d plus 15. Divide through by 5, so 3 vt is equal to 2d plus 3. So therefore, the stationary point is going to occur when t is 2d plus 3 over 3v. I'm not going to go into finding the second derivative to show that it's a minimum. We can see that there is no maximum value, but you could argue that there could be a local maximum, I suppose. Although when you look at the function, you see that it's actually going to be d squared is a quadratic in t squared. So that does actually mean it's a happy quadratic, it's going to be a minimum. So we'll give min since d squared quadratic in t squared. I'm trying to say that, I think hopefully that makes sense anyway. Like y equals y equals x squared essentially, except we've got d squared equals some quadratic in t squared. And the coefficients are positive, so it's going to be one of these. Okay, I'm not going to justify that anymore, and in fact, the mark scheme didn't expect that. So min occurs when t is equal to 2d plus 3 over 3v. Actually, very close now. So remember, we've got d squared in terms of t. We've worked out the value of t that gives the minimum, and we know that it's always going to be greater or equal to 4. So I can sub in. Turns out, actually, that it's going to be best to sub in for 3vt, because here I've got 2/5 times 3vt, so I can say 2/5 times 2d plus 3 minus d all squared. And then over here, I've actually got 1/5 times 3vt, so 1/5 times 2d plus 3. And turned it into a quadratic inequality in terms of little d. Let's expand this to make it a little bit more simple. So I'm going to have 4/5 d plus 6/5 minus d all squared. And in fact, no, let me do the whole thing. Plus 2/5 d plus 3/5 minus 3 squared is greater or equal to 4. That is going to end up being 6/5 minus 1/5 d squared plus, and then this is 3 is actually going to be 15 over 5. So I will have 2/5 d minus be 3/5 minus 15 over 5, 12/5. And I can actually take out the 1 over 5 from each expression, but remember I'm squaring it, and then I can times through by 5 squared. So what I'm saying is I can basically cancel this, and this out, and times this by 5 squared, or 25. Okay, that is the way to go. Expand the brackets, 36 plus d squared minus 12d plus 4d squared plus 144 minus 24d minus 24d, so that's minus 48d, greater or equal to 100. Add the like terms, 5d squared minus 6d d, that's 180 minus 100, so plus 80, greater or equal to 0. D squared minus 12d plus 16 is greater or equal to 0. Turns out this doesn't factorize. You might think after all of that, they'd at least give us one that factorizes, but it doesn't. So I'm going to set it equal to 0 and complete the square. You could also use the quadratic formula. Actually, completing squares is quite often just easier, to be honest. You have to sub in all these values and square them. Just d minus 6 squared minus 36 plus 20, so that's minus 20, which gives us it equal to 20. D minus 6 is going to be equal to plus or minus the square root of 20, which means d is equal to 6 plus or minus the square root of 20, which we could leave it like that. We could simplify to root 4 times root 5, so 2 root 5. Now we've got a positive, well, actually, they're both going to be positive because remember 6 is root 36, so I have 1 here and 1 here. The quadratic will look like this. And I'm interested, don't forget, this was an inequality. I'm interested where it's greater than 0. So it's going to be this side of that root and this side of that root. Therefore, d is going to be less than or equal to 6 minus 2 root 5, or d is greater or equal to 6 plus 2 root 5. The only other thing to add, and this is easy to miss, is that it says at the start that where does it say it? The light aircraft is behind the aeroplane, so we can't actually have d becoming negative, and therefore we also, sorry, jump back to the top, we also require d greater than 0. Since it says it's behind, they're not in line or anything like that. And therefore, finally, we've got 0 is less than 6 minus 2 root 5. Wait, what am I doing? 0 less than, I was just momentarily thinking, can it actually equal 0? But it does say it's behind. So 0 is less than d, which is less than or equal to 6 minus 2 root 5, or d greater or equal to 6 plus 2 root 5. Okay, very nice mechanics question there. Just very quickly, there is one other way to do it. Instead of differentiating, I'm not going to go through the whole process because you see how long my videos can end up being, but I will show you the mark scheme. So instead of differentiating and looking at the minimum and finding the like where the minimum occurs, we could go straight to the inequality, which is in terms of v, t, and d, multiply it out. I thought about doing this and I thought it's just getting very messy, but you can multiply it out. You get this quadratic in t and have it greater or equal to 0. And that is telling us that the discriminant, because this quadratic is greater or equal to 0, the discriminant will be less than or equal to 0. It's basically never going to intercept the x-axis, or the t-axis in this case. It might just touch it. So that's why we've got a less than or equal to. And if you put everything in, v squared minus 4ac, then you can rearrange it to this. Still quite a lot to do here. This, and you get the same quadratic, which we then solve. So have a go at that approach as well. You might prefer it. I think the algebra is just a little bit trickier, which is where the differentiation method comes into its own. But, they're both good methods. When you have quadratics and you're trying to find stationary points, differentiation is good. I would often complete the square if it's a nice quadratic. It just tends to be a bit quicker. But in this case, with all this algebra, I think it's quite easy to make a mistake. Anyway, that's another approach. Thanks for watching.